All right, everybody, we're going to be going over some examples from the gravitational potential energy that we covered on Monday. So that would look like the stuff from here, week 10, all right, potential energies, all that good stuff. All right, bear with me. I'm still working on getting back to the classroom, and this is now I can use the tablet, but I can't see it, so I have to be writing on something while staring at the screen, so it looks kind of weird. But all right, so here we have this setup. What is the change in the gravitational potential energy from A over to B? And we can see we have the mass right here, right? And it goes, so first thing if we're doing gravitational potential energy is we want to know what is the actual height. Where is 0? So we see 0 down here, so we're going to go and just make sure that this 0 we see where that's at. So B is at a height of 0. A is at a height of 5 meters. Okay, so if I go and do that, I can take a look at my formula sheet and know that the change in gravitational potential energy is equal to the force of gravity, mg, times the change in height. So now it's really just plugging in all of my stuff. I have mass, which we said is 40 kilograms, so 40 kilograms. G on Earth, I'm going to use, we can use 9.8, right? So you can say G is equal to 9.8, or you could be lazy. I don't think it's lazy. I think it's smart. And we can approximate G to be about 10 meters per second squared, which is totally okay to do on the AP exam. And the if we use 10 for G, it makes the math a little bit easier. Because now here, for this change in Y, let's use a little different color. This change in Y right here would be the final height, which is 0, minus the initial height of 5 meters. Okay. And let's go back up here. Now 40 times 10 gives us a force of 400. Remember, a kilogram times an acceleration, a mass times an acceleration would be newtons. And then 0 times negative 5, or sorry, 0 minus 5 would be times negative 5 meters. So far we have a Newton times a meter. So altogether this would equal negative 2,000. And a Newton times a meter would be a joule. So this negative right here, let's go, this is the hardest part, getting the different colors. The negative right here simply means that energy is leaving the system. And this would be gravitational potential energy is leaving the cart. So that's all that minus means. Remember, that means that it got transferred somewhere else. There's 2,000 joules of gravitational potential energy has gone out of the cart and into some other form of energy. Okay. All right, let's see. Let's take a look at this other one. A moon exploration robot lifts a 0.245 kilogram moon rock up a vertical distance of 60 centimeters. This action required 0.24 joules of energy. Solve for the acceleration due to gravity on the moon. Okay, so let's think about what we got. I'm going to make this, we'll make it thick. Let's just make this one thick too. All right, so a moon exploration robot lifts, so we have mass, right? We have a distance that it's moving, and then we know the amount of energy. So it's raising height. So that vertical distance right there, whoop, makes me think gravitational potential energy. Okay, so let's go down here and we're going to say, all right, the change in gravitational potential energy is equal to mg times the change in height. Right? We are being asked to solve for the acceleration due to gravity, which is g. So that's what we're trying to solve for. So let's isolate that variable first. If I rearrange these variables, I get g is equal to, that would be change in gravitational potential energy, all divided by m delta y. And now I just need to plug in my values. I know the change in gravitational energy was the amount of energy that it took, right? 0.24 joules. I know the mass was 0.245 kilograms, 0.245 kilograms. And the change in height was 60 centimeters. And let's see, it lifted it up. So that means it went from, can't draw that over there apparently. That's a height of 0, right? The rock's on the ground. And then it went up 60 centimeters or 0.6 meters to up here, right? So it went up 0.6 meters. And now we just plug that in. 0.24 joules, 0.24 divided by 0.245 times 0.6, 1.63. So G is about 1.63 in a joule divided by a kilogram meter. Right, we're doing a G in acceleration, so we should be meters per second squared. Let's just double check for funsies. Whoops. If I have a joule over a kilogram times a meter, right? A joule is a Newton times a meter. So right away, these little meters can cancel, and so I'm left with a Newton over a kilogram. Well, remember, a Newton is a unit of force, right? That's mass times acceleration. So mass is kilograms. Acceleration is meters per second squared, and then over kilograms. And now you would see that these cancel, and we're left with meters per second squared. So we're good. All right, and this is actually the acceleration of gravity on the moon. So everybody's happy. For this, what is the change in gravitational potential energy from A? And A is going to be down here to B. And B is going to be right there. Okay, so again, change in gravitational potential energy. So let's go our equation. Change in gravitational potential energy is mg delta y. And it's just really plugging and chugging, right? We know the mass is 500 grams. Now remember, this needs to be always in kilograms. So 0.5 kilograms. I would get 0.5 because there are 1,000 grams in a kilogram, so I would move this decimal 3 times. So that's 0.5 kilograms. G, we're kind of assuming this is on Earth, so we're going to say it's about 10 meters per second squared. Remember, you can use 9.8 there if you want. And Y, delta Y, it goes from a height of 0 up here. I forgot to draw what it is. Let's say it's 10 meters. Okay, so that would be a final height of, remember, delta Y is final minus initial. So we need to take the final height, which is 10 meters, and subtract the initial height, which is 0. And then 0.5 times 10 times 10 would be 50 joules. Cool. So that's kind of just some overall basic explanations of how to just find the change in gravitational potential energy or use that equation to solve some other stuff. So, all right.